And we are live. So who was Dr. Trees blaming at the beginning of the second half this morning? Because I transferred his videos for it, so I looked at him and he's saying something about like, I'll blame you because I did something like that.
Oh, because he was telling us that if we don't catch him, that he doesn't turn it on, and he would blame us for not telling him that he should turn it on.
I see. Okay. Got it. Okay. Same deal. Yeah. It'll be your fault, not my fault.
Blaming the students.
Exactly. That's right. Well, we're all much better at blaming other people than we are at blaming ourselves.
Good.
Some people are more that way than others.
I wonder who we could be referring to.
Actually, I wasn't thinking of anyone. Oh, again. Yeah, I see your point. You're looking like, yeah.
I'm trying to think. Politics?
Yeah, totally. Okay. And then some random person will be watching this video on YouTube and say, I knew they indoctrinated people politically in college. And it's not indoctrination.
It's
they're
the
already
liberal arts. Therefore, we're all liberals.
Exactly.
Yeah.
That actually is thought to be a marketing problem for small colleges, is people assuming that they're liberal because they're liberal arts. No, that's liberal as in freedom, not and free, not liberal as in.
Did you say free?
Yeah.
Did I miss this drop down?
Yeah, right. Choose your payment plan. Free. $50,000. Oh, I chose the wrong one. Sorry, you can't change it.
It's like every time you click the free one, it actually clicks the 50,000.
Yes.
They won't let you actually click that one. It's just a placebo.
Yeah. You need to have the special promo code.
Yeah.
Get that out.
How do you get that?
They should have that, and then every time you click it, it's a link to the Rickroll.
The promo code should be born wealthy. Free college.
All right, so let's study collapse of clouds. We're gonna make a mathematical model here. It has some simplifications, but it's more sophisticated than what you'll do on the homework, which is basically say, what's the acceleration at the surface of the cloud? If I assume that stays constant, how long does it take the cloud to collapse? And that gives you almost the right answer. But let's get a righter answer. So it still will have some simplifications in it, but it'll be righter than that extra simplification in the homework. But it's still kind of back. So when a molecular, and it's also when he says there's going to be these mathematical transformations, and I'm like, whoever did this the first time, how did they think of that? Yeah, it's not hard to understand it. It's like, how did you think of that? Why did you make that definition? Maybe they had a lot of experience with these things. But anyway,
Maybe it was aliens.
what's that?
Maybe it was aliens.
Yes, aliens, that's right, yes. So, as you joyfully show in the homework,
It's been a while.
at least Alec has already shown this.
Is this the third or fourth one?
I don't remember, but it's the one where you're comparing the pressure gradient to the gravity force and saying that it's essentially in free fall into the universe. As you joyfully show in the homework, when a molecular cloud begins collapsing, it is essentially in free fall until it becomes optically thick, because dPdr is much, much less than g m of r rho over r squared. Molecular cloud begins collapsing until it is optically thick. It is essentially in free fall. So it becomes optically thick once its density has gotten big enough. pressure gradient force, dPdR, much smaller in size than the gravity force on the little parcel. The gravity force per unit volume, gm of r rho over r squared. Pressure is a lot weaker than gravity, the force on each parcel. So it starts out essentially just in free fall collapse. And that means we're not in virial equilibrium, so we don't have this situation where half the energy released is converted into thermal energy and half is radiated away. It's all radiated away because it's optically thin. There's nothing trapping radiation inside of it. And so that means that it's isothermal. The internal energy stays constant. So as long as the cloud stays optically thin, in other words, it's essentially transparent to the photons it's emitting, all the gravitational energy released during collapse is radiated away. So the cloud's internal thermal energy stays constant. It's not building up internal thermal energy. This is not virial equilibrium. It is not converting half of its energy into thermal energy. It's all being converted into radiation. Emphasize that. Unlike when we have virial equilibrium. Wherein half the energy is converted to thermal energy. That ain't what happens here. Not surprising though, because remember, virial equilibrium means essentially that it is not changing with time, or it's collapsing slowly, that it's very close to being in equilibrium, so we can use the virial theorem as an approximation. Here, it's in free fall. It is not close to equilibrium. Since the internal thermal energy per unit mass is 5/2 kT for pure hydrogen 2, molecules have an additional kT of thermal energy associated with their vibrational and rotational modes. So instead of 3/2 kT average thermal energy, it's 5/2 kT. So since the internal thermal energy is 5/2 nKT, and the total number of particles, which we assume are all H2 molecules, quite right, but web. So for a diatomic molecular gas, it's 5 halves kT, 3 halves kT, like a monatomic gas, but then also another half kT for vibrational degrees of freedom, and another half kT for rotation. We'll probably talk about that in StatMech at some point.
Already did.
What's that?
You said we like just did.
We just did. Yeah. Can I just say, trees and me is like
Seriously. It like just dawned on me that I was like, wait, that 5 comes from degrees of freedom. What?
yeah.
We covered two things that we covered in Astro 1, the parcel of gas.
Oh, yeah, it was literally the same question.
Yeah.
Oh yeah.
We did the hydrostatic equilibrium derivation, and then we did, what was the second one today?
I forget.
I forget.
Yeah.
I think of it.
Yeah. Nice.
Oh,
I like
convection.
it.
Oh, yeah.
Oh yeah.
Oh, yeah. Good reasons for convection.
I like it. All right. Very good. Okay. So the temperature stays constant is the point of this, because the number of molecules isn't changing, and so therefore, since it's radiating away all that energy, the temperature stays constant if the internal energy stays constant. Temperature stays constant, the collapse is isothermal. We got ourselves an isothermal collapse here.
I'm not convinced that you guys didn't plan this.
What's that?
So I'm not convinced that you guys didn't plan this.
Well, you know what? We truly did not. Not that it would have been a bad thing if we had, but we truly did not.
Should be a prerequisite. Before this last.
For extra.
For us.
Yeah, well, actually, it kind of works out that you see some things here, and then the thermals are reinforcement / reintroduction, and vice versa. It's fine, as far as that's concerned, because I think I tell you what you need to know here, and then you can get more detailed derivations sometimes in the
Yeah.
Go.
Yeah. Like I say, it used to be that we didn't regularly offer StatMech, and so I would actually do a mini course of it in this class, but I no longer need to do that, so. All right. Yeah, I used to do like, well, you'll see it later, like the partition function in much more detail. We saw it before, but in other words, I used to derive the partition function and so on and so forth. If you're talking about the partition
We
function.
have indeed.
All right, I'm liking this more and more. We're just gonna team teach this. All right. Equation of motion.
We talked about that for like 2 days now.
Yeah.
Is we're just assuming that there's radial motion, it's only moving the r direction. So per unit volume, the force, the mass times the acceleration term comes out as rho d squared r dt squared. In other words, rho is the mass per unit volume, and so rho d squared r dt squared will be equal to, on the other side, the force per unit volume. Put another way, I could multiply this by a little dv volume element, and then rho dv would be the mass, and so dm times its acceleration would be the ma in Newton's second law, and then on the right-hand side we have to write the force. The force per unit volume is minus dpdr. We did this last semester, and the gravitational force, the pressure force per unit volume is minus dpdr, and the gravity force per unit volume is minus g m of r rho over r squared. So in other words, this is mass per unit volume times acceleration. pressure force per unit volume. Plus gravity force per unit volume. I say plus because of the fact that both those terms come in with minus signs. So both forces, minus dPdr is the pressure force per unit volume, and the gravity force points inwards, minus gm of r over r squared. Now the pressure force, the pressure gradient itself is negative, so the minus dPdr will point outwards in order to balance gravity. But anyway, as you joyfully showed in the homework, we can neglect the pressure term. So then we can divide through by the density and say that d squared r dt squared for any radius within the cloud, the little parcel of radius r, d squared r dt squared for that parcel is minus g m of r over r squared. So here's my cloud, which we're taking to be spherical, and r sub c is the radius of the cloud. And let's look at some little parcel at radius r. So that's what we're talking about. D squared r dt squared for that parcel is equal to minus g m of r, well, m sub r over r squared. M sub r is the mass interior to radius r, right? Because gravity only cares for spherical symmetry about the mass interior to your radius. And the point here is that as r decreases during the collapse for a given initial spherical volume, the mass interior to the shrinking surface stays constant. In other words, the cloud's collapsing, and this parcel, as it collapses towards the center, well, all the parcels that are closer to the center than it is, or at the same distance, they're also collapsing towards the center. So r is decreasing for that parcel, but the total mass inside of where it is stays constant because it's all collapsing together. So it keeps feeling a stronger and stronger force because it's experiencing gravity from the same amount of mass compacted into a smaller and smaller volume, is the idea. And this is where our model is different from what you do in the homework, where you just assume the acceleration stays constant. In fact, the acceleration keeps getting greater because it's feeling more and more gravitational force as it gets closer and closer to the center. So in other words, the actual collapse will be faster than what you would get from the homework problem. It will collapse faster because the gravity keeps getting stronger and stronger as the cloud shrinks, essentially. So as r decreases during the collapse for a given parcel, parcel of gas in the cloud, the mass interior to the shrinking surface stays constant. The mass interior to the shrinking spherical surface on which it lies stays constant. board there, so I'm going to come over here.
Get that exercise.
What's that?
Get that exercise, run back and forth, reverse and forth.
Yeah. All right. So we can write. I was actually thinking that I was thinking this is a pretty good exercise. That mass interior radius r is equal to 4/3 pi rho naught r naught cubed, where rho naught and r naught are the initial values of rho and r for our parcel. The values they had right when the cloud started to collapse. We're assuming that the cloud just, all of a sudden, we kind of let it go when it starts to collapse. So initially nothing's moving, but then everybody's feeling gravity, so they start going, all falling together. Okay, so does that make sense? The point is that at any given time, the mass interior radius r is always 4/3 pi rho r cubed. It's always volume times density. The point is that as it collapses, the mass interior to the parcel stays constant. So r and rho are really changing with time for our parcel, but the mass interior radius r is always what it initially was, namely the initial volume times the initial density. And that stays constant as it collapses. So this gives us a relation, in other words, between r and rho as it collapses. As r shrinks, rho has to change in just such a way that the total mass inside stays constant. It tells us how the density depends on the size of the cloud as it collapses. Okay? And we move on. This gets pretty clever, actually. I like this derivation, so it's pretty clever. So, especially when it's like, and now we make this substitution, like I said, and I'm like, I see that it worked, you're really smart, you know. So, multiply both sides of the equation of motion by the velocity of the surface of the sphere, by the velocity of the parcel, I'll just say.
I was about to continue the trend and then you shot it. Okay.
I shot a glance. And what we're doing actually parallels the derivation of the work energy theorem. You do exactly the same thing when you derive the work energy theorem for a particle acted on by a force. So we just multiply both sides of the equation over there, the d squared r to t squared equation there, by dr dt. So dr dt, d squared r dt squared is equal to minus, so let's put in that m of r is 4/3 pi rho naught r naught cubed, and then I'll multiply by the g that's there as well. So gm of r, in other words, is minus 4/3 pi g rho naught r naught cubed. And then we've got a 1 over r squared, and we multiply by dr dt. So I multiply both sides by dr dt, and I've expressed m of r as 4/3 pi rho naught r naught cubed. That's how those two relations or equations relate to one another. I've got dr dt now on both sides because I multiplied through, and I put in that m of r was 4/3 pi rho naught r naught cubed. Yes?
So this might be a dumb question, but are we allowed to put the DRDTs on opposite sides of?
I'm just, you mean like on the left on one side and on the
Yeah.
right? Oh, yeah, because this is like saying 3 times 5 is the same, basically, DRDT is just a number at any given time, so I'm just,
Yeah.
so this, it's, 3x is the same as x times 3, is what it comes down to.
Yeah, I've had too much other math where.
Yeah.
doesn't work.
At any given moment, the RDT is just some number, and so it doesn't matter whether you multiply a number on the right or the left. Uh-huh. Right, now I can see how you think, oh, it's calculus, is this some weird thing? No, just remember DRDT is just a number at any given moment. So, well, another way to put things is DRDT is the v, the velocity of the parcel. D squared RDT squared is dv dt of the parcel. So let's write this as v dv dt is equal to minus 4/3 pi g rho naught r naught cubed 1 over r squared drdt.
I get what you're saying, I guess you could write it like that, but why is that the first thing that comes to your mind?
Yeah, oh wait, we're not there yet. We're not at the part where it's like, what the? This isn't so bad because at this point, if you go back, this is really the what we're doing right here is exactly what you do to prove that work equals change in kinetic energy. So this is something somebody would think of just because, it's not on the top of your head, but actually the work energy theorem is derived in exactly this way. So again, it's not, maybe I wouldn't necessarily immediately have thought of doing this, but no, you just wait. We're not at the part where it's like, how the heck did you think of that? We're not there yet. Okay. So this is separable, right? Just multiply through by dt and then integrate both sides. The integral of v dv is equal to the integral of minus 4/3 pi g rho naught r naught cubed times the integral of dr over r squared. In other words, I multiplied through both sides by dt to get rid of it. So it's just v dv is minus 4/3 pi g rho naught r naught cubed dr over r squared. Now let's integrate both sides. So what's the integral of v dv? Yeah, half d squared, right? Which we'll write as drdt quantity squared. Plus 1/2 drdt quantity squared. This is what I'm getting at with work energy theorem. In other words, if we multiply by a mass here, this would be 1/2 mv squared, right? And on the other side, it's essentially the gravitational potential energy type term, because we've got the dr over r squared, gravity force type of thing. So this is, what we're going to get is essentially going to look like work being, or change in kinetic energy is change in potential energy kind of thing. But it's not really our goal here. It's just a step along the way. So 1/2 drdt squared is equal to, so the integral of dr over r squared is minus 1 over r, right? Minus 1 over r. So the minus will make that a plus. So this becomes 4/3 pi g rho naught r naught cubed times 1 over r plus c, where c will be a constant of integration. Right? When you integrate both sides, you have to throw in an integration constant that we will evaluate. So we'll use initial conditions to figure out what C has to be. Setting dr dt is equal to 0 when r is equal to r naught. In other words, the cloud isn't moving when it's just beginning to collapse. So at the initial moment when nothing's happened yet, and when the radius of the parcel is still its initial value r naught, it wasn't moving. dr dt was 0 at that moment. And then right afterwards, it started collapsing because of gravity. So setting dr dt equals 0 when r is equal to r naught gives C is equal to minus 4/3 pi g rho naught r naught squared. Right, because if I do that, I'm saying that 0 equals minus 4/3 pi g rho naught r cubed times 1 over r plus c. And so then I just solve for c. 0 equals all that. So c is minus this when I plug in r naught is equal to r. Well, r cubed over r is just r squared. So no, I should say r is equal to an r naught. So this means, what I really meant to say is this r becomes r naught. So r naught cubed over r naught is r naught squared. Set it backwards, but same thing. So let's put that back in, that c is equal to that. And let's solve for dr dt. In other words, we'll take the square root after moving the 2 over there. So dr dt is equal to minus 8 pi over 3, because I multiplied by the 2 to get rid of the half, g rho naught r naught squared times r naught over r minus 1 all to the 1/2 power, because I took a square root. So notice this first term here I've just factored. In other words, I've rewritten r naught cubed over r as r naught squared times r naught over r. And then the c is, when I multiply by 2, I've got a 1 here because the c then was the term that's going to give us a minus 4/3 pi g naught, g rho naught r naught squared. So it comes in that term. Yes?
How did the negative come out of the square root?
What's that?
How did you get the negative out of the square root?
Oh, I forgot. So I took a square root, right? And the square root, there's a positive and a negative one. We choose the, if I meant to say this, yeah, so thank you for asking that. We choose the minus square root because the cloud is shrinking, so therefore dr dt should be negative. So, but basically there's also a solution where it's expanding. Guess what? It turns out when we do cosmology, we're going to choose the positive root because you can make a Newtonian, so to speak, cosmological model that is exactly this, except that it's expanding instead of contracting. Expanding and slowing down because of gravity. But here, we want it to collapse, and so we're choosing the negative square root. Negative root chosen since cloud is collapsing. Okay, so now we're going to do some relatively obvious, if you will, transformations, and then we'll do the one that's like, what? Okay, so to find r of t implicitly, turned out that we can solve for this thing that's related to R explicitly, and then R is implicitly given by that. To find R of t implicitly, set, we're going to define theta to be R over R naught, so dimensionless, in other words, it's just R divided by its initial value. So when theta is 1/2, for example, the cloud is half as big as it started out. And big K is going to be equal to, just to save writing, 8 pi over 3 times G rho naught, since that shows up over there. So just to save ourselves, we'll write with, with the square root as well. Because over here, we have a square root of 8 pi over 3 G rho naught. So just to keep things nicer, we'll do that. So then notice that if we take R naught d theta dt, then that is R naught times 1 over R naught dr dt. Because R naught's a constant, so if I take d theta dt, that's dr dt over R naught. So R naught d theta dt is equal to dr dt. So dr dt on the left-hand side over there can become R naught d theta dt. And that'll equal with our definition of K minus K times R naught times 1 over theta minus 1 to the 1/2 power. So we've rewritten our equation like that using our definition of theta and our definition of K. Because notice the R naught over R over there is 1 over theta on the other side. So of course you look at that and you're like, how can I solve that equation? And what immediately does not at all suggest itself, at least to me, is to make the following transformation. Now said, this is what I was promising you, let's define theta to be equal to the cosine squared of, and you know what, the book uses C. But I hate that damn letter, so let's call it Y. I'll just try to remember. I put it as C in my notes because that's what the book uses, but that letter is so hard to write if you haven't practiced it. I'm better than I used to be at it. Let's call it Y here. So theta is cosine squared of Y. It's not obvious to me that it's useful to define theta to be the cosine squared of Y, but it turns out it's great. It does wonderful things. Again, it's not hard to follow, but so in other words, we're implicitly defining Y, to be the inverse cosine of the square root of theta, right? If you undo it, right? Cos Y is the square root of theta, so therefore Y is the inverse cosine of the square root of theta. A fact which we will use in a bit. So that d theta dt is, so what's d theta dt here? Notice the chain rule says d theta dt will be d cosine squared y, how do I put, I said, how do I? Let me think here. I've got it. So d d theta dt, yeah, will be d cosine squared y dy dy dt, right? Yeah, d cosine squared y dy dt from the chain rule. And what's the derivative of cosine squared y? Well, let's put it like this. I'll add another chain in there. So d cosine squared y d cos y d cos y dy dt. Right? Bad algebra, but good calculus, as my intro calc prof used to say at Case Western Reserve. So what's the derivative of cosine squared y with respect to cosine y? What's the derivative of x squared with respect to x? That's really what I'm asking. 2x, right? So what's the derivative of cosine squared y with respect to cosine y? 2 cos y, right? So this will be 2 cos y times, what's the derivative of cos y with respect to y? Minus sine y, right? And then dy dt is just dy dt. So d theta dt then is minus 2 cos y sine y dy dt. Which is why we made that transformation. To it. That's equation 1. So 1 becomes, notice here the R naughts cancel. I didn't explicitly cancel, but the R naughts cancel. So d theta dt on the left-hand side there is minus 2 cos y sine y dy dt. That's the left-hand side. And the right-hand side is minus k times 1 over cosine squared y, because theta was defined to be cosine squared of y, minus 1 to the 1/2. You find what I'm selling? Whoops. Minus. Yeah, thank you.
Does it all the time? There's a better one with the parentheses.
Yeah. Well, let's rewrite that as minus k times 1 minus cosine squared y divided by cosine squared y to the 1/2. Just putting them over a common denominator. Oh, but wait! What's 1 minus cosine squared y? Sine squared y. So this becomes minus k times sine y over cos y. Also known as tan y, but we don't care about that because we've got a cos y and a sine y sitting on the other side there. So just write it as minus k times sine y over cos y because I'm taking the square root. So, and board free here. So therefore, what we can do is say that we're going to cancel the cosine y's and multiply through by cosine y on both sides, and say that cosine squared y dy dt is equal to k over 2. Multiply, so I canceled the sine y's. I've got a minus on both sides, so that cancels out. I'll bring the 2 over to the right-hand side. I'll take this cosine y and match it up with that cosine y and make it a cosine squared. So the reason for the transformation is to get the equation into this form, because then I can multiply through by dt. It's separable. I integrate both sides. So not hard to do, but how did somebody think of making the transformation that was going to lead to that in the first place? That's the thing. That's, again, maybe this is somebody who, just did differential equations all the time and they'd seen something similar before or something like that. But in any case, break time.